You know that very well. And we have completed many of the portions of the chapter, and very few things about this chapter left. Very few. So probably and based on that, whatever the topics we will be discussing in this class. So to my knowledge, probably this will be the last topic of this chapter. So let's carry on with that topic, because once this topic is over, almost we will be almost completing this chapter, and then we can move ahead with the further chapters. All right. So today we will be doing a very interesting topic, which which is almost required for, or rather, in most of the reactions, and the knowledge of this particular uh, rather topic is very important. The topic is basically redox reactions. The topic is redox reactions. Now, what is redox reaction? Details of the redox reaction, then that we will definitely rather discuss in detail as the lecture goes on. But before going to that's mentioned over there, and before going to that, for another thing, perspective which we need to analyze, that is why we will focus on this particular topic. Okay, so I always tell you all that whenever you read a new topic, try to figure it out that why you are reading that particular topic. What is the importance? Because whatever the topics are given, whether it's in any subject, there is some application. Because just for only increasing the general knowledge, those topics are not given. Hence, try to figure out that one. It will help you out to understand many rather things which are going around you, and also it will develop the your interest rather, because once if you are able to relate between whom between the topic and the work and the things which are going around you, you will see that more interest is coming up. It will be more interesting. The study, the topics and the entire subject will be more fun. Okay. Now, redox reaction is quite important because the reactions actually give us the information, or this topic actually give us this information, that what sort of reactions will take place, which element can react with another substance. So possibility or feasibility of a particular reaction, this is a very important information which can be derived from this particular redox reaction topic. Now, not only this, which particular reaction will take on, moreover, the what should I say, the maybe the reactivity. Yes, of course, the reactivity of a particular metal or an ion, or those things also, such informations are also available through these redox reactions. Now, the point is, this application, this information is very, very important, because such information will help us to prepare, rather into design many applications in our daily life. For example, the uh, making of a battery, that means a galvanized cell or electrical cell, the batteries. Redox reactions are very important important tool over there. The next is we are having, for example, we are having a particular stain, and if we know that which, rather, which two compounds or which element is there, and whether that particular compound or element will react or not, based on that, we will be able to develop or to consider chemicals which will react with the stain and will remove the stain from the particular place. So there are numerous applications of this particular topic. Okay, so let's carry on. Obviously, the first question, based on the topic itself, the first obvious question is, what do we understand by redox reaction? That's a very obvious and a general question. A very simple answer to this question is the reaction in which oxidation and reduction of an atom takes place simultaneously. It's called a redox reaction. It's a very, very simple definition. You can just see that one. That the reaction in which oxidation and the reduction of an atom takes place simultaneously. Now, over here, this atom maybe basically symbolizes not only a neutral atom. Over here, this particular atom, what I mentioned over here, this actually represents neutral atom as well as non-neutral atoms. Okay, if some atoms are charged or some species are charged, so the ions, the cations and anions are basically derived from a particular atom. So based on that particular concept, the word atom is representing both neutral as well as charged species. So the reaction in which oxidation and reduction of an atom takes place simultaneously. Simultaneously means at the same time. So oxidation will also take place, reduction will also take place, but both will take place at the same time, or maybe one after the another. So this particular definition is a very simple one, and it's giving us a very clear idea that which particular sections or which particular points are being focused or the highlighted in redox reaction. Of course, as we know that or rather a definition is accompanied by an example. So we have considered this example Fe2O3 plus carbon, or this can be coke also. So carbon is there and it is giving product iron. So over here carbon is getting oxidized. So the oxidation process is taking place with risk or rather with carbon. So oxidation process is taking place with carbon and reduction process is taking place with iron. So we normally say that carbon is getting oxidized or carbon has been oxidized and iron is being reduced or reduction is going on with iron. So with iron reduction is going on and with carbon oxidation is going on. Similar. So now with if you another one example over here, hydrogen is getting oxidized. So oxidation, this process is accompanied with hydrogen, and with copper, reduction is going on. So copper is being reduced, whereas hydrogen is being oxidized. Now, if you see one thing, there is a one particular that is this oxidation and reduction. If you notice, both are occurring at the same time. Now, you may, with the first definition, or some of you may have that idea or conception that one particular atom only will undergo oxidation as parallelly reduction. No, there has to be minimum two components, or there are also species, there are also procedures where one component is on the one side being oxidized and on the other side getting reduced. Now, such reactions will always, so oxidation and reduction will always involve minimum two products. Remember this. So oxidation and reduction will involve minimum two products because within one particular compound, or it can be an element, whatever. So the based on the reactant side as well as with the product side, if you compare, and if on the reactant side there is particular, what should I say, particular one compound or one element is there. which is and which is forming after the decomposition or anything, which is forming two compounds or three compounds. But there has to be two, three compounds, because the same component cannot give, suppose from one compound or one component giving to one compound. So there cannot be that same species is undergoing oxidation as well as simultaneously reduction, and same for the both the, and it is happening both in the same compound. So it's not possible. It is not possible. So either there has to be two reactants, uh, there is an option, but there has to be two products. That's compulsory. So minimum two products. So two reactants not compulsory, but two products it has to be. Otherwise, such oxidation and reduction reactions are not possible. The same thing happening with the copper and hydrogen. As you can see, that copper is getting reduced and hydrogen is getting oxidized to water. Now, oxidation and reduction, which I gave you in terms of the definition, that's basically what is oxidation, rather. That definition I gave you, oxidation reduction. Now coming to the word redox has been derived from the word reduction and oxidation. Okay. Now the obvious question, what is oxidation and reduction? That's an obvious question. Now there are many definitions. Okay. The definition which I follow, generally, that is that I mentioned over here. But apart from this definition, there are other simple definitions which I have not stated over here. Okay, which, remember this, which I have not stated over here. The first that definition is about oxidation. That oxidation means addition of oxygen. Oxidation means addition of oxygen to a particular atom, and reduction means removal of oxygen from a particular atom or molecule. Okay, so I repeat, oxidation means addition of oxygen to a particular atom, and reduction means removal of oxygen from a particular atom. This definition was in terms of oxidation, or rather from terms of not oxidation, it was in terms of oxygen. Now reduction, this oxygen can be replaced by another element is there, that's called hydrogen. So oxidation means removal of oxidation means removal of hydrogen. So removal of hydrogen from a particular compound or an atom or a molecule, not atom, but from a particular molecule. Removal of hydrogen is called oxidation. Addition of hydrogen is called reduction. So removal, I repeat, removal of hydrogen is oxidation, and addition of hydrogen is reduction. Okay. Now, apart from this, the definition which I follow generally, that is, oxidation equals loss of electrons by an atom of an element, and reduction means gain of electrons by an atom of an element. So the previous definitions which I gave you in terms of oxygen and hydrogen, they are different. This definition is in terms of electrons, which I personally use when I determine oxidation or reduction. So oxidation, I repeat, as you can see, loss of electrons by an atom of an element. Reduction means gain of electrons by an atom of an element. That is reduction. If you remember that previous example which I have given earlier, over there we have seen that iron Fe2O3, that reaction, iron was written reduction, that means iron was getting reduced and carbon is getting oxidized. So if I consider this, if I want to explain that phenomena in terms of this definition, then I will say that carbon is losing electrons, for that reason it's getting oxidized, and iron is gaining electrons, for that reason it is undergoing reduction. Now the meaning of this is, this indicates, what does this mean, this above the two, oxidation and reduction? This indicates that if an atom after losing electrons increases its oxidation number, then it is considered that the atom is undergoing oxidation. And if an atom after accepting the electrons decreases its oxidation number, then the atom is undergoing reduction. Understand this very, very carefully. The meaning, or the, what should I say, the information, what the above two statements or definition of oxidation reduction are giving, what's giving information? This indicates that if an atom after losing electrons increases its oxidation number, then the atom is undergoing oxidation. So just now I said carbon was losing electrons and hence it undergoing, or rather it went under oxidation. So in terms of this, we can say the oxidation number of carbon has been increased, and if an atom after accepting the electrons decreases the oxidation number, so iron, which is undergoing reduction, decreases. That means the oxidation number of iron and in Fe2O3, an oxidation number of iron and the reactor in the product side, there has been a decrease in the oxidation number and hence undergoing reduction. Okay. Now automatically once again another question is popping up. What is oxidation number? So questions one after another. What is oxidation number? Oxidation number is basically valency of an atom or molecule expressed with its electrical charge. So molecule valency of an atom of an element or a molecule expressed with its electrical charge. Now the question is, valency and oxidation number are same, because over here it's written that valency of an atom of an element or molecule expressed with its electrical charge. Now valency, basically, if we consider the integral value, or the integral value of oxidation number and the valency, then in terms of that, valency and oxidation number, the numerical values will come the same, only on numerical. Okay, numerically the values will come the same, but are the same. But the point is, between oxidation number, we are incorporating another one factor, that is electrical charge of the entire molecule or of an element or of an atom, not element rather, or an atom or a molecule. So this particular incorporation of electrical charge is not present with valency. In valency, the number only counts. In valency, if you remember the definition, there is basically the count in numbers, that how many. So it's basically a quantitative figure. In valency, it represents the quantity. If I say the valency of hydrogen is 1, valency of hydrogen or chlorine is 1, or it is of, for example, calcium it's 2, or maybe phosphorus it's 3, or nitrogen 3. Then basically, these 1, 2, 3 in terms of valencies, it basically represents the quantity. That means it will give an idea that how many electrons will either, or rather how many electrons will are there to participate in a reaction to form a chemical bond. Okay, so how many participate in the reaction to form a chemical bond? So how many electrons will participate? It can one electron can participate, or 2 electrons, or 3, or 4, or 5, or 6. So based on that, how it's a quantitative number. But what about for oxidation? We are over here considering that the electrical charge, basically the electrical charge, since they're over there, we considered about how many electrons. Now, along with that, how many, we are incorporating the total charge of the entire total charge of the electrons. So if three electrons will participate, so oxidation number, we are also incorporating their charge as well. So there will be -3. So 3 electrons, each electron is of -1 unit negative charge. So 3 electrons will represent -3. So if 3 electrons represent only the valency, so 3 represent the valency of an element, or sorry, valency of an atom, then definitely -3 will represent the corresponding electrical, include the electrical charge. So -1 with respect to each. So 3 electrons will -3 charge. Okay. So we're just incorporating along with the quantity how many electrical, or so how much electrical charge. So total electrical charge is also getting incorporated in oxidation number. Clear? All right. Now the example, of course, that oxidation number of sulfur in H2SO4 is +6. Oxidation number of chlorine in HCl is -1. This basically gives an information. The information is, it suggests that oxidation number of an atom can be either positive or negative, right? Hence, valency without plus or minus sign will be considered as valency. So if a valency, if any integer how we can differ between valency and oxidation number is, if a particular element has been written that the oxidation number is this, or rather with no only 3, then we will consider, or 4, we will consider that one as valency. Including the sign, so once the signs are being included, whether it's a plus or it's a minus sign, if those two signs, any one of the either is included, then we will consider that particular integer value as oxidation number. So oxidation number includes the sign, and the valency doesn't include the sign. So plus and minus, I repeat, this plus sign and minus sign is compulsory for representing oxidation number. So please do not write, I repeat once again, please do not write the oxidation number of sulfur in H2SO4 is 6. Oxidation number of chlorine in HCl is 1. It's not correct. Then it will represent the valency, not the oxidation number. So if you write that, it will be marked incorrect. So oxidation number of sulfur in H2SO4 is +6. So you have to give this plus as well as this minus, whichever is applicable. So there is another way of stating this, that the instead of oxidation number, we normally also say that oxidation state of sulfur. The oxidation state of sulfur in H2SO4 is +6. Oxidation state of chlorine in HCl is -1. Oxidation state of iron in Fe2O3 is +3. So these things will surely. The next is how to calculate oxidation number. That's very important. How to calculate oxidation number, because if you do not know how to calculate oxidation number, then how can we state whether that there is an increase in oxidation number or a decrease in oxidation number? And if we do not understand if there is a increase or a decrease in oxidation numbers, then how can we state that whether it's an oxidation reaction or a reduction reaction? So now for calculating oxidation number, let us consider a molecule CO2. The question is calculate the oxidation number of carbon in this particular molecule. What's being mentioned over here? Remember, there are certain atoms whose valency remain almost fixed. Hence, according to the definition of oxidation number, the valency with electrical charge becomes oxidation number of that atom. Hence, the oxidation number will also remain fixed, right? if you go through the statement once again, that remember there are certain atoms whose valency remain almost fixed. It will not change. It's fixed. So it do not undergo variable valencies, or it not having variable valencies. So according to that definition of oxidation number, the valency with electrical charge becomes the oxidation number of its atom. Based on that, metals exhibit positive oxidation number, and non-metal exhibit both positive as well as negative oxidation numbers. So metals always exhibit positive oxidation numbers, and non-metals always exhibit both plus or minus oxidation number or oxidation states. So it can be both, or rather it exists in both, as a depends upon the situation, as if it can be a plus or it can be a minus. So metals exhibit positive oxidation number, and non-metals exhibit negative oxidation numbers. Sorry, positive as well as negative. I've separated that one to highlight this thing. You have to remember that one, okay? Now, these are fixed oxygen. I'm giving over here the oxidation states, or the oxidation number of atoms, or sorry, ions basically. These oxidation states are only applicable for when they're in the ionic form. That means in molecules or in compounds. So during that time, these oxidation states will be applicable. Otherwise I'm counting that one. So oxygen minus 2, so don't mess up. Oxygen minus 2, this is only when oxygen is in a compound. Okay, this oxygen is in a compound. Hydrogen, that also is in a compound. Sodium in a compound. So this sodium is having +1. The sodium is having +1. This is basically for any compound of sodium. Calcium +2. This oxidation state is for calcium compounds. Fluorine -1. Fluorine compounds. These oxidation states are valid only when these atoms are in a molecular form. Molecular form means in compounds, not is existing as a molecule. For example, hydrogen, H2 we are writing. So H2 is basically a molecule, so you will still say this is also a molecule. So this should have, this hydrogen atom should have +1. No, that's not. Molecular form is in compound form, when they are existing as compounds. So for that we are having that molecular form. Else, they all will be having zero oxidation number or states if they're in their elemental form. Elemental form, that means stable elemental form, stable. So oxygen stable elemental form is O2, hydrogen stable elemental form is H2, fluorine stable elemental form is F2. So all these will be having oxidation states 0. Sodium elemental form, only sodium is Na. Calcium, that's a metal, so elemental form is Ca only. It's not Ca2 or Ca3. So they will also be having oxidation states, oxidation number 0. So for the molecule CO2 we were calculating, let the oxidation number of carbon be Y. A molecule is always electrically neutral. Remember this. Remember this. It has been underlined over there. It has been marked number in bigger level alphabets. A molecule is always electrically neutral. So it's having no electrical charge. A molecule is always electrically neutral. So the algebraic sum, it's not a simple arithmetical sum, it's stated over there. So the algebraic sum of the electrical charge of the molecule should be equal to 0, which actually corresponds to the oxidation number of an element, of an atom. Electrical charge, we know that the electrical, we stated that one earlier also, that we have incorporated this electrical charge along with the valency, so to make that one as an oxidation number or oxidation state. So the algebraic sum of the electrical charge, the total, that means algebraic sum of the electrical charge of the molecule, that means a molecule is comprising of atoms. Molecule is comprising of atoms, so the electrical charge of all the atoms within the molecule the algebraic sum of that is equal to 0. Let us find it out. So the total electrical charge contributed by carbon in CO2 equals Y. So only one carbon atom present. Hence, Y is the oxidation number, oxidation state, including the charge. The total electrical charge contributed by oxygen in CO2 equals to 2 oxygen atoms, and each having an oxidation state of -2. So that's giving a total of -4. So oxidation number of oxygen in molecular form is -2, and there are 2 oxygen atoms in CO2. For that reason, 2 multiplied by -2 equals -4. Hence, therefore, Y, which is a oxidation or a total electrical charge in the oxidation state of carbon, plus total of -4. I said algebraic sum. So we will algebraic sum means minuses will be there, but we will add up everything. So Y plus, we are doing sum, so plus, and with that, how much we are adding? -4 we are adding, and the total should come to 0. And hence with that, we can say Y equals to +4. So there was this much algebra. I hope it's very simple to you, all of you. Now for another example, H2SO4, calculate the oxidation number of sulfur. This example I've given previously, but it's stated over there is +6, how it's +6, let's find it out. The total electrical charge contributed by oxygen is 4 oxygen atoms are there. As you can see, 4 oxygen atoms, and each of -2, so total electrical charge -8, including the charge and the quantity. So oxidation number of oxygen in molecular form is -2, and there are 4 oxygen atoms in CO2. Sorry, there's a printing mistake. It's not the CO2. I typed that one wrong. Please don't that. It's basically a typing mistake. It will be H2SO4 over there. 4 oxygen atoms in H2SO4. There is a typing mistake over there, so ignore that one. So 4 oxygen atoms in H2SO4. So the total electrical charge contributed by hydrogen is 2 into +1. Hydrogen is +1. I've stated earlier also, 2 hydrogen atoms are there. So oxidation number of hydrogen in molecular form is +1, and there are 2 hydrogen atoms in H2SO4. Hence, let the oxidation number of sulfur be Z, and hence +2, which is for hydrogen, Z, which is for sulfur, and -8, which is for oxygen. So the total of the electrical charge should be correspond to 0. So 2 plus 2 minus 8, that's simple algebra you can solve, so Z equals +6. If you notice that each and every place I have added, or I'm giving this plus sign or the minus sign, because I'm stating that giving the sign is mandatory. Calculate the oxidation number of chlorine in HCl, HClO, HClO4, HCl. Simple way now, not to write so much. We know, since we know everything, just we will write the statement that let the oxidation number of chlorine be Z, and this formula HClO followed by that. For hydrogen it's +1, chlorine is Z, and oxygen is -2, so Z equals +1. For HClO4, so +1 for hydrogen. We will write that one in bracket because we've got to do algebraic sum. We have to do algebraic sum. So plus Z plus 4 multiplied by -2. 4 multiplied by -2. So that's giving +7. So oxidation state of chlorine in HClO4 is +7. And with HCl, we are having +1 plus Z, and it's -1. Oxidation number of Fe in Fe2O3, H in H2O, it's a simple one, the same thing. 2 multiplied by Z plus 3 multiplied by -2. The Z is coming +3. Let the oxidation number of hydrogen be Z. So 2 multiplied by Z plus a -2, you can see Z equals +1. So now if we consider that example which we have discussed in the first example, the reaction one, about redox reaction, you remember this one. So what there is stated, carbon is getting oxidized, and carbon and iron is getting reduced. So we can verify this. So carbon, as I said, the elemental form is having 0 oxidation state, and carbon in CO2 is +4. This one we have calculated. So plus 4. Hence, oxidation. As I said, increase in the oxidation state or oxidation number. Increase in the oxidation number is oxidation. Fe2O3, it's a reduction. As you can see, plus 3 to 0. So there is a that means reduction or decrease in the value of oxidation state. So plus 3 to 0. Plus 3 to 0. So it's a reduction. So decrease in the value of the oxidation state. Copper oxide, the same thing, 0 to plus 1, hence oxidation. And from this is plus 2 to 0, reduction. So with this, I hope this oxidation and reduction and this redox reaction, the concept is clear to all of you. So that's all for today's class. And stay home and take a very good care of yourself. Thank you. And for further queries and questions, you are free to ask. Thank you so much.